Welcome to this edition of the Simon's Observatory video update, where we have research scientist Nicholas Galitzki live from the UC San Diego High Bay Laboratory to give us a bit of an update. How is it going over there? Tell us a little bit about what it's like being able to get into the lab and work.
Yeah, no, it's great to be able to get in here and continue to make progress. And I can give you a little bit of a walk around. This giant thing behind me is one of our telescopes. It's the second of 3 units. It's still in a box because we haven't had the amount of people we need here to actually open it up and start work on it. But we're hoping to get that amount of people in the lab soon, hopefully this month, but we'll see.
What's the protocol for working in the lab now?
We actually have here posted our sets of rules that we have to do. But at UCSD, we're in what they call orange phase. And the main part of that is obviously PPE. I have to be wearing a mask in the lab, gloves, disinfecting a workstation when we leave. Let's see here. In this lab, we're allowed 3 people, and we have zones marked on the floor, which I can actually show you. I'm in the shipping zone. I've a graduate student who's in the mid zone, but let's see. There we go. That's the line. Let's see here. What other protocols? Oh, we have to fill out a symptom screening every day. So every morning we get up and check if we have any new symptoms, report that to UCSD, and that gets us clearance to come into the lab. So kind of continuous checks like that. And trying to think of what other little things we did. Obviously we got wash your hands a lot, just be conscious of that sort of thing. We've got bottles of disinfectants and hand sanitizer just kind of roaming the lab. But yeah, that's mostly what it means, and it allows to get a few more people in here than before. So now I'm coming in 2 or 3 times a week, and before I was coming in maybe once a week just to check on equipment that we have here. Yeah. Oh, I can't hear you.
Considering the barriers, there's been some major milestones that you've met in the last couple of weeks. Starting with the halfway plate, getting that thing running. Tell us a little bit about that.
Yeah. So I'm going to wander on over to the camera we got running. It'll be a little noisier over here because it's currently cooled down. But there we go. Right. So we've been able to do a cool down, which is basically we test new equipment at the cryogenic temperatures it's supposed to operate at. Right now, the focal plane on this guy is sitting around 50 millikelvin, 50 to 100 millikelvin, so a fraction of a degree above absolute zero. What you were talking about, the halfway plate, that's in this top section here, and it's a magnetic loving spinning device. Actually, there's one other person in here today. There we go. Bryce, who's actually working in here to work on that and continue to make some improvements to the electronics on that, so that mostly we can do some remote work. And the remote work we're doing is running the first few pixels for the Simon's Observatory and really testing what we call the readout system, our electronic system that allows us to record data from our focal plane to a computer disk. And it's a fairly involved process involving a number of wiring, routing, amplification stages to different temperature stages, and this is our first good chance to understand how that whole system works inside an actual camera. So this camera, that one, will be going to Chile in hopefully about a year, although schedules being what they are these days.
That halfway plate was a real team effort. I mean, I want to emphasize how many people worked on that. It's got its own, control unit just for the levitating rotor mechanism to keep it spinning. And I know that was a lot of work to get that to work. And I'm really happy that it's really reached its nominal functionality.
Yeah, no, we got it spinning, and so the getting up to spinning was the first big milestone there. It spins at about 2 hertz. It's big. It's, you know, I can actually show you. It's about the same diameter as these guys, and it spins around at 2 hertz inside this cryostat at cryogenic temperatures at 40 Kelvin. And yeah, that was a huge milestone. So this is I brought it up because I'm pointing there. That box right there. That houses all the electronics. It's open right now on the bench because we're still making some improvements to it. But yeah, it was a huge milestone to get it running. And now we're trying to do the next big thing with it, which is have it running while we're also reading out the detectors to understand if there's any coupling between the two, and start really understanding the performance of the whole system. So baby steps, but it's been great to be able to get into lab and continue to make progress on these items.
So the other thing that's been going on is you're now at a point where, you know, you've got some pixels working and you've got some detectors working. Is that right?
Yep. So in this cool down, we have what we're calling the single pixel box, and that's a little bit of a misnomer because it actually has more than one pixel in it, but it's a test device we made as a collaboration that has. It's an enclosed metal box about this big, and it has a chip in it that has a number of what we call pixel elements. Basically, there's a full pixel element. They're not coupled to any light source. They're in an enclosed box, but we're able to run our readout electronic chain through it and basically read it out as we would a pixel that we would be using in observation, right? And so it's the first test of what does the electronic signal, what are the noise properties of the pixel, and how does it interact with its environment? How does it interact with the RF environment, the magnetic environment? We're going to do a vibration analysis where we shake everything and see if there's pickup in that. And so there's really understanding the properties of the pixel itself, the devices, so that we can really right now it's debugging. It's trying to figure out where we might have issues, what we might need to improve. Kind of tweaking things before they make the full arrays of pixels that will actually be used to observe the CMB.
So what's next? What are some of the next steps that are going to be? I mean, we've got the face-to-face coming up here, so we've got a couple more weeks before that, and then the summer's now happening. Quarter is over. Students they're already gone now. Classes are gone too. But what's going to happen over the summer?
Well, in the near term, I'm kind of excited about one thing that I get to try out. Taking it really in here now. This is, hold on, there we go. If you can look down here, maybe. That's our window. That's hard to see, but this guy in here.
Yep, we see it. Good shot of it.
So that's the window that will go on the SAT to actually allow us to couple optically. So our next cool down, I want to install that along with a bunch of filters, and that'll be one of the big tests of whether we can, the big first step towards coupling the SAT to light. So to actually make it a telescope, right? It needs a window so the light can get in. So that's one of the first big steps that we're taking. And then kind of the next step after that is our colleagues in Japan are building all our optics. So they have these silicon lenses and a number of other components that will actually focus the light. And we're hoping to install that, I think, right now at the end of July, which again, pending a few schedules actually coming together like we want them to. But we're hoping that'll arrive at the end of July. That is a major installation. The optics assembly weighs over 100 pounds, I think. Significantly over 100 pounds, maybe approaching 200. And it's a big assembly that will have to be installed in that. So that'll be our kind of next huge operation. And once we have that in there.
How many elements are in that?
We have. So in the optics, it's a self-contained cylinder of aluminum that's it's about this big around and a little over a meter high, and it has these 3 silicon lenses that are being made at University of Michigan, University of Chicago.
Yeah, so wasn't that one of the limiting factors? Was that they had to grind that, right? They had to actually cut with a special jig to the wavelengths those silica lenses.
Yeah, the silicon lenses are big challenges. So that's what actually focuses the light so we can observe it. And what makes us a telescope. And they have to be precision ground and shaped to our requirements. And then after that, because they have a high refractive index, if we have to apply a special surface treatment to them called an anti-reflective coating. A lot of people have those on their glasses as well, just to make sure that the lenses don't reflect the light; they refract it. And so that treatment is what's the last step that's just being finished up now that some of these labs are opening up. And once they finish that in Chicago, they're going to ship it to Japan. Japan does the final assembly of all the elements, checks that it's not just the shape that we have to really care about, but it's also the positioning. And a lot of the assembly in Japan is making sure that the position of the three lenses with respect to one another is exactly what it needs to be. They do all that testing, and then they ship it here to San Diego, where we actually put it into the telescope and start coupling it into pixels and going to the next stage of testing past that, where we can actually couple two light sources in the lab.
When you receive that, we'll do another check-in. That'll be very interesting to see the before. Just the unboxing of that'll be fun, and then the installation. Maybe in a month we'll do another check-in with that, and also maybe I can get the folks at University of Chicago and University of Michigan to give us a little rundown of what that was like. They must feel really good about getting that out the door.
I'm sure they do. It's a lot of fun, and their equipment is amazing to cut those lenses. So it's always worth looking at. Oh, thank you for chatting with me.
Thank you, Nicholas. Thanks for the video update, and we'll be getting back with other folks, other collaborators from the Simons Observatory soon, so everyone can see what's going on.
All right, great. Thank you. Bye.